This thing then. Good evening to the folks here in the room with me and to anyone watching on the recordings in YouTube. Hello. My name is Whitney, or Whit. I am a GRE, GMAT, and executive assessment instructor here at Manhattan Prep. So all of the tests for business school and the big test that y'all are all here for pretty much any graduate school. I love these free prep hours. They give us an opportunity to talk about topics that we rarely have time for in a class setting. And in fact, I almost don't always have time for these in private tutoring. And so these are topics that either come up in questions asked to our website or that we see kind of floating around in our classes or with our own tutoring students. And so this evening, I wanted to tackle a topic that I just don't think we've done as much of as I would like, especially with how common the area is on the GRE. But we're going to look at geometry, all of the things with geometry. I have done a lesson in the past about how to learn geometry, particularly how to use flashcards. So if you have not, if you're still kind of early in your studies and you haven't started making your flashcards and you haven't started learning all of the geometry formulas, that's a great lesson for how to commit them. We will talk about geometry formulas tonight, but we're going to focus on geometry within a very specific question type. We're going to look at quantitative comparisons. So we will look at that one very specific question type, and I want you to start to think in the back of your mind, compare, don't compute, right? So a lot of times for QC, we're going to actually do math, but the GRE is not a math test. The GRE is not a math test. The GRE is not a math test. Okay, so math comes up. It can be important, but overwhelmingly, the GRE is testing our ability to think creatively with mathematical concepts. And quantitative comparisons is the perfect outlet for that because we might not actually have to do a lot of computation. And we'll see how that plays out tonight. Welcome. So I'm here in Durham, North Carolina, where it is god-awful hot. It is miserably hot. It is summer. And I have a couple of dogs wandering around, so you might get to see one of my dogs. I'm not sure whether I should apologize or say you're welcome. But we're going to get going. So just to let you know, all of the books that we'll be working, or all the questions that we'll be working on this evening come out of our GRE 5-pound book. And so you can purchase that directly from us. I think our portal actually even just like puts you into Amazon, or you can go direct to Amazon and find any of our books there. 5-pound book is a really nice add-on to your studies. Unfortunately, the ETS folks who write the GRE just don't put a lot of questions out into the world. There's very few. There's only the official guide that's quite small. And then there's a supplement for quant and verbal that are also even smaller. So very, very, very few official questions available. And so one of the biggest complaints before this book ever came out was that there were no practice questions. Well, we've got you covered. We've got over 2,000 practice questions organized by topic. Across all the different question types, quant and verbal. There's even some diagnostic at the front and some advanced questions should you want to attack them. So we'll be working from questions out of this 5-pound book this evening. You can find all of them, again, ebook or physical book, pick it up anywhere books are sold. I always feel a little bit like advertising. Anyhow, we're going to jump in. So we're going to start with this idea of QC. So here's the deal with QC. QC will be the first, let's call it 6 to 8 questions that you'll see within each quant section. Now, QC always looks mostly the same. So it will always have 2 quantities, quantity A, quantity B. And the answer choices will always be the same. So answer choice A is where quantity A is greater. Answer choice B is where quantity B is greater. Answer choice C is when they're equal, and answer choice D is when we can't tell. So one thing I like to make very, very clear, because I don't think it is clear, at least not early on, is that these first 3 choices really imply always, right? They really imply this concept of always. And I say that because one of the most powerful tools for dealing with QC will often be choosing numbers and plugging in. And so if I'm thinking about plugging in numbers, I'm only going to pick answer choice A if for all the numbers that I can pick or I can imagine, quantity A is going to be greater and then same for B, or I'm going to only pick C if I can show that they are always equal. Now, that should bring up for you this idea that like, wait, what do you mean all, like, do I have to use every number under the sun? And the answer is no. The answer is no. What we're looking for is a pattern, or we're looking to like break the relationship. So we're going to start with an outline tonight of how to attack QC. So even if you've been doing GRE studies for a while, I find that a lot of my students, again, even when they find me months into their studies, a lot of my students just are not using a really formulaic process for QC. And so we're going to do that tonight. We'll also encounter a couple of QC strategies. There are several that are out there, things like hidden inequality, cheat off of B. These we've got entire free prep hour videos available for on our YouTube channel. So the link that I shared with y'all here in live lesson with me, or if you found us on YouTube, then you can check out our entire list, our entire playlist of videos. But we've got a bunch on very specific QC strategies. So tonight we'll start with the generic strategy that we'll use for all QC problems, regardless of content, be they geometry or probability or word problems. Yeah. So first step for, I'll be honest, any math problem, not just QC, is what I like to call a first glance. The first glance is nothing fancy. It's an opportunity to just see what you're given. So sometimes in QC, we'll be given what's called upfront information, and that'll be information that appears up here. So it'll appear above the two quantities, and we'll see a bunch of it tonight. There's tons of it, but it'll be information that appears above the two quantities, and it will be information that I need to use to try and either solve something about the two quantities or compare them with one another. So this will be given factual information that I will need to utilize in order to assess my two quantities. So my first glance is going to involve stuff like, is there upfront info, right? Like I just even want to know, right? Like upfront info. Some other things that I like to notice, are the quantities similar? This would be a perfect case where they are similar. We will see some other questions this evening where the quantities are maybe a lot more different. So for example, if we were to see, and we will, when we see this problem, notice that we have upfront information. And in this case, our quantities are not at all similar. In fact, we have another kind of cool thing that we want to be looking for, which is quantity B what we'll call simple? This is for a technique called cheat off of B. We'll use this idea of, is quantity B a simple value? In this case, it is a simple value. And this shows up more than you might expect, right? Quantity B is a simple value. Quantity B is a simple value compared to quantity A. Again, still upfront information. Quantity B is a simple value, and so on and so on and so on. So a lot of times, quantity B is a simple value. This is a very well-known technique of comparing against quantity B. Yeah. So I want to know, what kind of information is there? Is there any? Are the quantities relatively similar, or maybe quantity B is very simple? And then I also want to look for any keywords or content clues. So geometry can be really nice. I see a triangle, I see a circle, I see coordinate plane, I see it. But maybe it's that I see words like average or median, probability. I see distances that would make me think a rates and work problem. I see ratios, I see the percent symbol, right? But what I'm thinking about is, what are some clues? Right? What are things that might give me the beginnings of an idea of what's being tested? Yeah, okay, so I love this question that showed up in the chat window. Thank you, Megan. This is a phenomenal question. When we start to get into shapes, and I'm going to talk about this as we encounter each one, diagrams can always change. So as we encounter geometry specifically, what we want to know is that, or what we want to understand is that the test writers cannot lie to you. So if a line looks like a line, it's a line. Or let's say you have a line and on it are the points A, B, and C. All right, A, B, and C. This is pitifully drawn, but still. So the points A, B, and C. Then it cannot be the case that it's actually A, C, and then B. The points have to be in the order that they came. If a line looks like a line, then it's a line. If a circle looks like a circle, then it's a circle. But, for example, they could draw a circle. They could put a line right here. But unless they tell you that it goes through the middle of the circle, you can't assume that. Now, if they tell you that this line goes through circle P, and they show the line go through the dot in the middle that's titled P, then you know that that line is the diameter. It's the distance across our circle. So they can't lie to you, but they absolutely will mislead you. So in the example of our line, it could be that A, B, and C are relatively evenly spaced. It could be that B is actually very close to C. So we want to be very cognizant of the fact that they would lie to you. It is, yes. If they, well, and they don't even have to tell you technically that P is the center of the circle. Anytime you're given a circle with a dot in the middle and it's named, that is the center. So if I called this circle P, then P is the center of the circle. But they do often make things explicit. Right. And typically they'll even call something a circle. They don't just assume that you know it's a circle. They'll often say, you know, circle P. They'll label it, they'll title it. But yeah, exactly. Now there are inferences that we can make, but we don't want to make assumptions, and those are different. So assumptions would be things that based on my eyeballs, I'm just going to guess that my eyeballs are telling me the truth. Inferences are conclusions that I can draw, which is based on what I was given, right? Like what pictures I was given or what formulas I know, I can then get other information that I can prove based on it. Inferences require that we understand geometric shapes and the formulas that go with them, not just our eyeballs. That said, if something is in coordinate geometry, that is the one place where they will not lie to you or mislead you. So anything that's in coordinate geometry is always going to be drawn to scale because it kind of has to be. The same thing would be true for anything that's drawn on an actual number line where they show tick marks. The spacing has to be true if they give you a number line with the actual spacing. If they just tell you that the points A, B, and C are on a number line, you don't have to trust that. Like you shouldn't trust it. But great question. Thank you, Megan. That's a great question. Okay, so now let's jump into our step 0, first glance. What do I notice about this problem? I don't see any upfront information. The quantities are actually kind of similar. They look a lot alike. They're both pretty simple. Quantity B is obviously not a number. And I would say that this is something to do with exponents. That would be my content clue here. Often in this world of content clues, I will categorize, at least initially, questions as story, mathy, or geo. So this would be a very mathy problem. A story problem would be anything that has a noun in it. Shoes, people, money, books, right? Anything that's got a noun would be a story problem. Anything that does not have a noun, and so there can be words in a math problem, it just might feel a little more like theory. It'll sound like a math proof. And then obviously geometry is geometry. Okay, so once we've got our first glance sorted out, our first step, and here's my big thing about just quant in general on the GRE, is this idea of, can I be curious, right? Can I be curious and try and, instead of assuming that I'm supposed to know something, try to determine whether, is there a way to know it? So I'm going to phrase these next 2 steps in terms of a question. So step 1, so now that we've kind of like taken in big picture of the problem, step 1 is, can I simplify? And this is a step that I think is pretty imperative that most people skip. sadly. So there are technically 3 places that we can simplify. We can simplify in the upfront information. We can also simplify within a quantity. So I may be asked to find the area. Quantity A is the area. So I simplify by figuring out what the heck the area is. I can also, from time to time, simplify across the quantities. And so this is a technique called the hidden inequality. And again, we've got an entire YouTube video directly about the hidden inequality. So if you're looking for that technique of how do I simplify by moving things from one side of, like, from quantity A over to quantity B, or from quantity B over to quantity A, or just canceling them from both quantities, we've got an entire lesson about that one too. All right, hidden inequality. Oh, that's supposed to be an inequality. There you go. Hidden equality. No, hidden inequality. Okay, so can I simplify? If I can, I will. Simplify can use things like estimation, eyeballing, algebra, thinking about extremes, right? Like, these are all ways that I can simplify. Once I've simplified things as far as I can get them, my next step is to ask the question, do I need to pick numbers? At which point I'm going to plug stuff in. If I do need to pick numbers, what I'd like to do is, my goal is to prove D. So in other words, if I have to pick a set of numbers, I am going to try and pick numbers so that I can show at least 2 different scenarios. Can I show that one of the 2 quantities is greater, and then I can show that the other one is? Or maybe I can show that the 2 quantities could be equal, but in some situations they're not. Or maybe I show that quantity B is greater, and then I show that they're equal. I don't need to show all 3. I just need to show 2 different relationships so that I can escape the always. Okay, so when I prove D, there's a nice little trick, and it's called zone F. It's probably one of my favorite tricks that we have. So zone F stands for 0, 1, negatives, extremes, and fractions. So this is our zone F. We use zone F to help us avoid the most common traps. For us mere mortals, the most common traps are to assume that everything is positive and everything is an integer. So zone F is really here as a bit of a battle cry, as opposed to like a checklist. It's like zone F, like I want to make sure that I'm picking things that help me prove D. And so it's just a reminder, right? I don't necessarily have to go through and like, make sure you pick 0, make sure you pick 1, make sure you pick negative. No, it's just to remind me of the different qualities of numbers that I would want to pick. Now, what happens when I'm trying to prove D and I'm being creative, right? In general, what I'll do is step 1, pick any number and see what happens. Step 2, try to prove D. So I'm actively looking for some way of proving D. So again, my first choice is just like roll the dice. Let's just see what happens. I'm going to pick any number that makes sense. I'm not going to think too hard about it. Just pick something. Once I've picked something, I'm going to try and prove D. If I fail to prove D, so if I'm failing to get there, like I keep getting the same stupid answer, it's like B again, and it's B again, and it's B again. If I keep getting the same stupid answer, then really what I'm doing is at this stage, I'm kind of admitting to defeat a bit. So my rule is like, just choose. And then like, you know, like just be open to a pattern. Just be open to a pattern. So if you keep getting the same thing over and over again, you might consider, well, like, why am I getting the same thing over and over again? Is there something fundamentally true about one of these quantities that's just going to keep making it bigger? So I can stop testing numbers. Like, I get it now. I see why this quantity is just always going to be bigger. Or I see why these quantities are always going to be the same. right? But if I can't, if I don't see a pattern, no big, I'm gonna just choose. So my rule of thumb is usually like right around three cases. Okay, I'm gonna test it out. That's about it. Yeah, okay, so great question in the window. Some QC problems are like tedious. Is there always a shortcut or pattern to avoid tedious calculations? So one of the things I would say is that some of this might depend on your definition of tedious. Yes, there are going to be times where we just have to compute. Geometry can often be one of those where we're just like slogging away at something. It shouldn't ever be just like massive number crunching. So you shouldn't be breaking out your calculator and doing a ton of combining of numbers in a calculator. If that's what's happening, you've missed something. But as long as you recognize how much energy is being put into steps 0 and 1, what you might find is that you don't actually end up with as much computation as you thought. We're going to see some great examples of avoiding computation in geometry. I love that. I will say there's another one, and this shows up. It's not going to show up really as much tonight. Although I might be able to grab a couple of questions to see if I can throw in at the end. But one of the things that does show up from time to time is this idea of extremes. And I find that this concept can be really helpful in the sense that if I make numbers really extreme, or we talk about this a lot, like rubber band geometry, like to the point that Megan was making, that we can't always trust our eyes. We have to imagine, like, well, what happens if we make this shape really narrow and wide versus what happens if we make this shape really like symmetric? So there are times where I can use this concept of an extreme to save me computation. So I could imagine the world, well, like, okay, what if I make this shape so infinitely long, but in order to do that, the height of it disappears to almost 0, right? Like the area of that thing is essentially going to disappear. I'm going to almost turn it into a line. And so I may not have to do computation on one end, like, oh, wow, I could really maximize this shape. I can make this shape really, 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 really big, or I can make the shape really, 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 really small. And then I can just compare. We will see at least one example of kind of that playing with rubber band geometry. But yeah, sometimes it's like, that's the luck of the draw. We do have to do a handful of computations or simplifications, but it's rare for you to have to crunch a ton of numbers. That's very rare. Okay, so for a problem like this one, I want you to type to me privately, what do you think the answer is here? Which quantity is bigger? Is it A? Is it B? Are they equal? Or is it that we cannot tell? So maybe send that one to me privately, just so it doesn't pop up in the window. But what do y'all think? Quantity A, quantity B, or I have no idea. I love what I'm seeing coming in so far. Beautiful, y'all. Nice. So all the answers that have been shared with me look great. So I know that I heard from many of you before the session started that you've been at this at least for a few weeks to a few months. And really strong work, y'all. If I think about my different cases, right, if I start with, I mean, I can't really simplify, let's be honest, like x and x squared, there's not much I can do. And so I'm going to start testing out numbers. If x is 0, right, then quantity A is 0 and quantity B is also 0. That would make the two equal. Same thing would happen with 1. But if I picked like x is 2, quantity A is 2, quantity B is 4, I now have a situation where they're not equal. Quantity B is bigger. And so I was able to show two relationships. I could show how they were equal. I could also show that depending on the numbers I picked, I could make B bigger. Because of that, I'm going to choose D. You might have also proven D by using a fraction. If x is a half, then quantity A is 1/2. Quantity B is 1/2 squared, which is 1/4, which is actually smaller than a half. So I get into the habit, if the two quantities are equal, I circle the equal sign between them. I always use this notation between them. It'll help out as you start to practice the hidden inequality, just to get in the habit of it. But if I can show that they're equal, I write the equal sign, I put a circle around it. If I can show that one of the two quantities is greater, then I will circle that quantity. And essentially what I'm looking for is I've circled different stuff. I've circled in the middle, I've circled on one side, or I've circled on both sides, kind of thing, just to keep myself organized. All right, so our correct answer is D. The relationship cannot be determined because depending on the value of X I choose, I get different answers. So let's do it. Let's jump into some questions. We will start with some basic rules of geometry. In general, we want to spend about a minute, let's call it minute 15 on QC problems. Some of these can be a little, more laborious than others or have more steps. But I'm going to set a timer counting up. Please send me your answer to just the host and panelists. Our goal is to get an answer to this question in around a minute 15, maybe up to like a minute 30. All right, if you're still working, that's totally fine, but I've got a handful of answers looking good. And always, if you are approved for extended timing, just keep that in mind, right? If you've been approved for time and a half, you'd be, looking more at about a minute 45 to 2 minutes for each QC problems. If you were awarded double time, so like 2x time, you would then be looking at more like 2.5 to like somewhere between 2.5 and 3 minutes. All right, so we need some formulas. So the interior angles of a triangle, so this is a great place to grab a sheet of paper. If any of these are formulas or rules that you don't know, add them so you can flashcard them. So the interior angles of a triangle add up to 180 degrees, which means each one of these angles, since they are all equal to A, this is what we would call an equilateral triangle. Which means that each of those angles equals 60 degrees. The interior angles of any quadrilateral add up to 360 degrees. Because they are in fact all the same angle, it must be the case that each one of these is 90 degrees. They did not have to give you the box in the corner. Now note, if they had not given you any angles here and they made it look like a rectangle, that doesn't mean it's a rectangle. Doesn't mean that those angles are actually 90 degrees. Or just because the sides of a triangle look equal, if they hadn't given me all of those A's, I wouldn't be able to trust it. At this point, I know that A is 60, B is 90. I'm going to plug it in. So 2 times 60 plus 90 versus 3 times 60 plus 90 over 3. And so I'll just kind of do my math here. 120 plus 90. I'm not using calculators at this point, but you absolutely can. I would practice your kind of basic mechanics. If these are really, really ugly numbers, sure, I might break out my calculator, but for now, 3 times 60 is 180 plus 30 is 210. There we have it. The two quantities are equal, right? So I had upfront information. The quantities were relatively similar. This is definitely a geo problem. And then can I simplify? Yeah, right. I could simplify the upfront information. Once I did that, I was able to simplify within the quantities. What that meant is that I got to an answer and I never needed to pick numbers. So I never had to get down to our step 2. That never happened. And that's going to be the case. Sometimes we're never going to simplify. I mean, sometimes we're never going to pick numbers just because simplifying worked. Got us all the way where we wanted to go. Yeah. Okay, great. So let's try it again. Let's go this route. And again, upfront information. Check in the quantities. Can I simplify? What does that look like? And we'll take a peek. All right, so this one took a little bit longer. That's okay. Upfront information, we've got triangles. I don't see any real numbers given. The quantities are, I can't really cheat off of B, so to speak. Quantity B is not a simple number. I'm looking for it to be a number, not like a variable. So can I simplify in the upfront information? I can, right? I can. This is definitely a line, which means that the two angles that form a line are equal to 180 degrees. So this whole thing is 180, which in other words means that this angle right here is 180 minus D. And this is going to be a really common construction, 180 minus D. Now, I will say this. Let's, for just a moment, because this is a known rule, let's call this little angle X. So what do I know? I know that X degrees plus D degrees is equal to 180. I also know that X degrees plus A degrees plus B degrees is also 180. In other words, I know that if I have to add D to X to get 180, or I could add A plus B to X to get 180, then it must be the case that D and A plus B are the same. And so what this would be is like a thought of like a remote angle. So notice that D is the exterior angle at this triangle. It will always equal the sum of the opposite, or like the remote interior angles. But let's say you are like me and you're not a memorizer. And so like memorizing this for you is like, no, thanks, I'm good. I don't want to memorize that. We can, right? So that we would show that these two things are equal. What we could do instead is go back to that first step and make this missing angle 180 minus t. So here's what I know. I know that A plus B plus 180 minus D, if I add all those angles up, it'll give me 180 degrees. From there, I'm going to subtract 180 from both sides. So A plus B minus D equals 0. And then I don't like that minus D, so I'm going to move to the other side. It's also nice because that's the two different values in my quantities. A plus B is equal to D. That means I know for a fact that they're equal, and I can pick C. We certainly could pick numbers, but that's going to take us a lot longer. So in general, for geometry, we will often get a long way with some simplification up front, even with some estimating and eyeballing up front. As much as we can, we'd like to do that, only because picking numbers for QC in geometry can be a little bit, right, to sort of quote the earlier question, it can be a little bit laborious, right? Batard was like exactly right. We can avoid some tedious computations if we're getting a little bit better at simplifying up front. All right, let's take a look at the following. I want you to notice again the sort of similar relationship to the last question. This time, still have upfront information, but we do have a simple cheat off of B situation. So if we didn't know how to simplify the upfront information, or we weren't sure how to get information about quantity A, then maybe we could use this like quantity B as a cheat. But I still want you to try and simplify. So I'll give you a timer. Let's take about a minute, 15, and then we'll chat about it. All right, and if you haven't given me your answer, go for it. Let's make sure you've got it. All right, so I'm looking to compare my two values, yeah? And so in order to compare my two values, I wanna try and get them to look more alike, So let's use that same trick. This angle right here, right? I don't have any of the inside angles. So this angle right here is 180 minus B. This angle right here is 180 minus C. And this angle right here is 180 minus A. Now, if I were to add all of these to one another, the sum would be 180. So I'm going to add 180, 180, and 180. If you want to add that all up together, you can. I actually normally just leave it as 180 minus A plus 180 minus B plus 180 minus C. All of that is going to equal 180. So what I'll do first is I'll subtract one of the 180s from both sides. I'll add the other ones. Go ahead and handle it. 360 minus A minus B minus C. And so if I add the A, B, and C all to the other side, I'm going to get that their sum is equal to 360. And so this A plus B plus C is 360. That actually makes quantity A bigger. How else could I get at this? Well, here's what I know. I know if I were to think of these little corners as X, Y, and Z, for example, I know that if I were to add A plus X and B plus Y and C plus Z. So if I were to add up all of these, so I added up A plus B plus C and X plus Y plus Z. If I added them all up, each pair is 180. So that would be 3 times 180. However, this X, Y, and Z right here is 180. So I know that most of this, that 3 times 180, one of those 180s is the inside of the triangle. So the outside of the triangle would be the other 2 180s, making that quantity bigger. A way that you might be able to get to it just a little bit faster, like looking for some shapes and like ways of seeing the relationship maybe a little more comfortably. Fact is if you didn't see it that way, that's okay. It doesn't matter, right? Like if you see it either way, I would say either method gives you plenty of time to solve. All right, what happens if maybe we don't get a picture or some information is missing? Let's try this one. All right. So a little bit of differing opinion again. I love it. So the perimeter of a square, so if they tell me a square, then that means that all 4 sides are the same. The perimeter of the square is 50% of the perimeter of this other square. So let's say I am going to just jump into picking numbers. So I could make up 2 squares. So in one situation, let's go with the perimeter is 50%. So that would mean if this one had a perimeter of, let's say 2, 2, 2, 2, so what, 8, then this one would have a perimeter of 16. And so it would be 4, 4, 4, 4. That means that the area of the small square, this is W, the area is length times width, or side squared. In this case would be 2 squared, or 4, over the area of square D, which would be 16, is 1/4. That would make them equal. I'd want to try one more that maybe was a little bit weird. And so maybe I would do 1, because weird stuff can happen around 1. I don't really feel like doing this with a fraction, but I could do this around 1. So this one's 1, 1, 1, and 1. That's a perimeter of 4. That would mean this bigger one has a perimeter of 8. I already know what that one was. That was 2's all around. The area of the small one is 1. The area of the large one is 4. I've got the same one again. I'm not sure that I really want to test another one. So I'm going to say C for this one, that they're equal. Something else I can do, though, is that the perimeter is side plus side plus side plus side. So that's 4S. So whatever this thing is, the perimeter of W is 4 times the length of the side. So I'm going to leave it an S for right now. The perimeter of D is going to be double that. So the perimeter of D is going to be 8S. And so now what I want to remember is that the length of each side is going to be equal. So I have 4 sides. That means, again, in this case, the length of each side was S. In this case, the length of each side is going to be 2S. So the area of square W is going to be side squared. The area of square D is going to be 2S squared. That's going to then equal S squared over, now I have to square everything, 4S squared. My S squareds would cancel and give me my 1/4. So this would be a place where if I could simplify it, if I thought about how to put it into my formula, I might avoid picking numbers. But notice that when I pick numbers, that didn't take all that long. One of the biggest things I want you to take from that is that a lot of times you can be flexible. I find that a lot of times students get really frozen by like, oh gosh, you know, I don't know how to do it besides this one way, and there must be another way, or like, which is the best way? And sometimes the best way is just to get going. It's like just to get started. What do I do though? Let's try another shape. Let's try circles. What do I do in this case? So this is not the diameter of the circle. This time I have upfront information. My quantities are not simple. In fact, my quantity B, although it has pi, is a simple value. If I needed to estimate, pi is 3.14. So I could say that this number is, 9 times 3.14, but it is a sort of simple value. And so I want to keep that in mind as I start to simplify, that really what I'm trying to do here is see whether the area of the circle is, could I make it bigger than 9 pi? Could I have it be smaller than 9 pi? Is there a scenario in which it would be equal to 9 pi? So I may not have to actually compute. It might be enough to just say like, oh yeah, it could be way smaller. Oh yeah, it could be way bigger. So let's try it with this one. I'll get y'all a timer going and we can chat. All right, I'm starting to get it. I got a bunch of answers in even pretty early. So very nice, y'all. Why do they tell me that the AB is not the diameter of the circle? Well, it's because the diameter of the circle is the longest possible line that I can draw inside of a circle. No other, what they are called chords, no other line, chord inside of a circle can exceed the length of the diameter. That means if 6 is not the diameter, then I know the diameter is bigger than 6. So if I want my formula for the area of a circle, and so my formula for the area of the circle is pi times the radius squared. If I know that the diameter is bigger than 6, then I know that the radius is bigger than 3. So at its edge, right, let's pretend that the radius was 3. If the radius was 3, the area would be pi times 3 squared, or 9 pi. However, I know that the radius is greater than that. I don't have to pick a bigger number. I can just show that it will never be equal to 9 pi. It will always be larger than 9 pi, giving me the correct answer of answer choice A. All right, so we've seen some circles, we've seen some quadrilaterals, we've seen some triangles. I want to offer up a little coordinate. This one will be quick. We'll finish this one. I want you to have an answer to this one in about 30 seconds. We have upfront information. The two statements or the two quantities are very much similar. But this is going to be one that I sort of need to know it or I don't. So hit me with your answers to this one. All right, so when it comes to slope, slope is by definition the rise over the run. But slopes that are positive are going to go up to the right. The more steep, the more positive. So think about it a little bit kind of like a sundial. The steeper the line, the more positive that it is. As the line begins to flatten, it gets closer and closer to 0, so becomes less and less and less positive until it becomes a flat line, at which point the slope is 0. And it doesn't have to just be a flat line on an axis. Anywhere where I draw a flat line, it's 0. Once I move from 0 and I start to tip right side low, I've moved into negative slopes. As a slope goes from flat to a little bit, to a lot more, to a lot more, to a lot more, the steeper the line, the more negative it becomes. And so for something like this one, in terms of comparing, I don't need to know the actual slope. There's no points given to me here. What I do know is that line L1 is flatter, which means it's closer to 0, right? The more flat from either direction, I'm getting closer to 0, but it is negative and closer to 0. So negative closer to 0, and then this one is negative further from 0. So if I think about a number line, if something is negative and further from zero, that makes that number smaller. Here's where I have to be really careful. That means that quantity A is greater because it is less negative. So line L1 is actually less negative. Okay, so we can start to think of some of these as just a straight comparison. Had a great question about parabolas. Let's go with almost never. I've never seen one on a real test. I have seen them in practice questions, but yeah, essentially never. Never in a way that you need to know their formulas. This was a question about parabolas, if anybody saw it. Yeah, no, agreed. Totally agree. What if, what do we say, right? Here we are towards the end of our session. Let's just try something crazy, right? Let's just try something crazy. It'll be fun. Here you go. I'm going to set a timer. Remember, our job is to compare. Our job is to compare two quantities. They look awfully similar. Okay. We'll take a look. Hit me with your answer. I'll give you a little more time for this one. I'll let you take this one up to 2 minutes. All right, I let y'all run a little bit longer just because I have almost no answers. All right, so show of hands, right? Just give me a +1 in the window. How many of you are trying to find formulas? Trying to compute. Yeah, for sure. So a couple of lessons about a problem like this one. One, it's coordinate geometry, so I can trust my eyeballs. Good news. Second, if they ask you about something like area of a shape and you don't have a formula for that. So for example, there is no formula for the area of a quadrilateral. That doesn't exist. Right? There are formulas for specific quadrilaterals like parallelograms, trapezoids, rectangles, and squares, right? But there are no formulas for just like good luck area of a quadrilateral. And so there isn't one, which means I'm not supposed to be calculating that. So I'm supposed to compare these two, which means the parallelogram here is this thing right in here. This is my parallelogram. Right, that's my parallelogram. And my weird wonky quadrilateral is this part right here. Now they have some stuff in common. I would say the easiest bit they have in common is like all of this weird shape. But once again, that's a weird shape. I don't know how to figure out what that weird shape is. So when in doubt, and I had an instructor say this today and I loved it and I'm going to steal it. When in doubt, just think triangles. when you are not sure what to do with a geometry problem, ask the question, is there a triangle in there that I could use? And so there is. So if we look at our two shapes, the triangle on the bottom is shared by the two of them. This whole big mess right here is shared by both quantities. In other words, it's not making either quantity bigger than the other. We can ignore it. So I'm just gonna sort of like white box this all out. I don't care about any of this stuff underneath my coordinate. Which means what I'm trying to figure out is which of these two triangles is bigger. The one that includes the N, that's this one, that's quantity A. Okay, so just to keep myself straight, this is quantity A's shape that comes over here. And then I've got the one that has J in it. That's quantity B's shape. So look, I've got all these numbers. I could start to actually calculate the area, but wait a moment. The formula for the area of a triangle is 1/2 base times height, where in any triangle, I don't care how you draw it. Maybe you draw it like a normal looking triangle. The base and the height will hit each other at a 90-degree angle. Maybe you've got a right triangle, at which point the two legs are your base and your height. That means that that would be them, right? I don't need, they hit each other at this right angle. If my triangle is wonky, this is the one that's got the B in it, this one right here, I could certainly draw a line, kind of like to be inside the triangle, but the easiest way to draw a base and a height in a case like this is often, because they'll often give you this measurement, if this is your base, then your height has to come from the angle across from it. I can't draw it inside of my triangle, and so its height is going to be this little vertical piece, right? So this actually becomes the height way over here. So what is the height? So the base of triangle A is here. The height of triangle A is here. So if I were to count it, it's what? 1, 2, 3, 4, 5, 6, 7, 8 is the base. 1, 2, 3, 4, 5 is the height. That said, the base of the triangle for B is right here. It's the same base. And the height is right. It's the same height. And so those two triangles, although they may not look like it, those two triangles are the exact same size. And so the area of the two quadrilaterals, since I've got the situation where this part is shared by the two of them, and then they each have a triangle above the x-axis that's the same size, these two quantities are equal. I didn't have to go in and try and like sort out the areas of all the pieces or try and come up with the formula because I was able to show, right, that area base times height, if they have the same base and the same height, our areas are the same. So we're often looking for these scenarios. I did want to show you one more, which was the idea of the extremes, kind of as promised. So let me give you one more problem, and then I'll send you on your way. Y'all are doing so good. I just want to make sure you have plenty to work on. So let's do here we go. Let's try this problem. All right, so I don't have all my answers in, that's okay. This is a place where no picture, nothing up front. Quantity B is a simple value, so it's very likely could be something we could cheat off of B. And quantity A is information about a rectangle. All right, so can I simplify? Well, the perimeter of a rectangle would be the sum of its sides. They just tell me what the sum is. They don't tell me what the actual side lengths are. So a rectangle could be like really stretched and skinny, or it could be perfectly symmetric. So one quick side note about quadrilaterals. Inside the world of quadrilaterals, what we've got are parallelograms. So let's just say we've got like generic quadrilaterals, right? Inside of generic quadrilaterals, we have trapezoids. We'll start there. A trapezoid is anything that has two parallel sides. That's a trapezoid. Inside of the trapezoids are parallelograms. Inside the trapezoid are parallelograms. So trapezoids have one pair, have at least one pair of parallel sides. To be a parallelogram, I not only have to have one, I have to have two pairs of parallel sides. So a parallelogram technically is a trapezoid. It's just a trapezoid where both opposing sides are parallel. Now, if my opposing sides are parallel and they're all the same length, so my sides are the same length, I have what's known as a rhombus. That's like the square that's tilted. If my parallelogram has 90-degree angles, then I have a rectangle. So instead of it leaning, it sits upright. I have a rectangle. And if I have both 90-degree angles and same length sides, I have a square. So technically, a square is a rectangle. A square is also a rhombus. So if they tell me that I have the area of a rectangle with perimeter 20, it could be a square. My rectangle could be a square. Okay. So maybe you have this little weirdo diagram that I just drew. Okay, so, right, all of these things are one another. The area of a rectangle with perimeter 20. So I like to use what we call rubber band geometry. It's like, how big can I stretch it or squeeze it? So I'm going to think of an extreme. I'm going to try and come up with a rectangle that has the smallest area possible. And then I'm going to come up with a rectangle that has the largest area possible. So typically, if I make a shape really, 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 really asymmetric, I start to shrink it. So if I wanted to have an area of a rectangle with perimeter 20, I would think of like an extreme, where essentially I made the length and the width like basically 10, 9.9999999, and I made them so skinny, right, that there was nothing left, nothing at all left for, I can't even write, so I'm just gonna leave it there, nothing left for the height, and the height's like 0.00000001. If I were to multiply 10 times this minuscule number, the area, meaning the space between those lines, would essentially disappear. And so I could come up with a rectangle that has an area of about 0. So I could certainly come up with a rectangle that's smaller than 30. The question is, can I come up with a rectangle that is greater than 30? And so what I want in that case is to be super symmetric. So if I have a perimeter of 20, then each side has to be 5, giving me an area of 25 my biggest area is still smaller than B. And so I'm going to choose B. B has to always be greater. You could prove it to yourself, like make these one bigger. So each one of these becomes 6. That would make each one of these have to be 4 in order to make it work. And 6 times 4 is 24. My area is going to start to incrementally get smaller and smaller and smaller, the more distorted or like asymmetric my shape becomes. But this is an example how an extreme can save you some computation. Like, look, I already know I can make it tiny. How big can I get it? Well, the biggest area still doesn't beat out my cheat off of B. And so I'm going to pick quantity B. All right, y'all, just so you know, as I mentioned, all of these questions are all in our 5-pound book. You can get them all there. Right? If you'd like more work on QC, we have a ton of really awesome free prep hours that teach a ton of different techniques for QC, from an intro to also thinking about all the ways that we can compare. So cheat off of B, hidden inequalities, right? Like all of these kind of like cool techniques that allow us to compare rather than compute. So if you are, also wondering, how do I avoid these crazy computations? Any of those video lessons would probably be awesome. We also have a couple of other videos on geometry, from learning the rules and making flashcards to specific lessons on just triangles or just circles or just quadrilaterals. So if you'd like a little bit more work in those content areas, check out the recording list in the YouTube channel. I'll also say that we have a ton of good video lessons for both quant and verbal across all types of questions and strategies. Your next steps, if you haven't and you still have some room out in front of you, by all means, you should come and access a practice test with us. We've got them on our website. You can just go to our manhattanprep.com. We also have a ton of free stuff on our site. And if you're still starting out, you can always attend a session 1 of any of our full course classes for free. So you can sign up and see what it's like, try out different teachers, and see which course in particular makes the most sense for you in terms of your time or time of day or what have you. Please, please, please come back and hang out with us. We have free prep hours a few times a month. Always a rotating cast of crazies that like to teach them. I know I speak for everyone else who teaches these, that they are some of our favorite things to teach. So yay, we like it when you come and hang out with us. Thank you so much for all of your your actions tonight, and all of your being active and jumping in and answering questions. I appreciate it. You made everybody's Monday night go by a lot faster. Again, my name is Whitney or Whit. You can call me either one of those. You can find me on our website. It's been a pleasure. Good luck with all of the rest of your studies, and have a wonderful rest of your night. Bye, y'all.